Have you ever wondered a very simple question when you try to remember the multiplication table and you encounter that 4 times 6 is 24. 3 times 8 is also equal to 24. So why, have you ever wondered, they are the same? In other words, why 4 times 6 equals 3 times 8? Well, you say that because both sides resulted to be 24. Well, that's the answer, but it's not a fundamental answer. When I say fundamental, we're actually trying to look at the building blocks of 4 times 6. In fact, if you think about 6, 6 equals 2 times 3. Right? So 4 times 6 equals 4 times 2 times 3. And this, using associative law, equals 4 times 2 first, equals 8 times 3. And by commutative law, equals 3 times 8. So in here, this process of actually going to the smaller building blocks is a way of thinking, and that leads to prime factorization. And prime factorization is really a process of factor those numbers into something non-factorable anymore. And this final state of getting somewhere that every term is non-factorable anymore is called a prime factorization. And the terms of those non-factorable terms are the primes. Okay? So in this class, we're going to talk about primes and this process called prime factorization. So what are primes? I'm sure most of you already know what are the primes. The primes are 2, 3, 5, 7, 9 is not a prime, 11, 13, 15 not, 17, 19, 21 is not, 23, 25 is not, 27 is not, 29, 31, 33 is not, 35 is not, 37, and so on. So what are primes? Primes are defined something non-factorable anymore. And in here, we don't include 1. For example, if you think about 2, 2 actually equals 1 times 2, and equals 1 times 1 times 2. And you see where it goes. Equals 1 times 1 times 1 times 2. And you can have arbitrary ones inside there. So, that's not very productive, and it's not going to be very useful, right? So mathematicians say, let's remove 1. We don't like ones in prime factorization. So 1 is not a prime. And what are primes? Primes are numbers a number, its factors are only 1 and itself. Okay, so it does not have any other factors other than 1 and itself. In other words, if you think about multiplication, these are kind of the building blocks. By that, what I mean is the following. For example, if you look at 12, 12 equals 3 times 4, right? We all know that. But the 4 is not a prime, can be further factored into 2 times 2. So this equals 3 times 2 times 2. Now, this you cannot do further factorization, prime factorization anymore. And this is the final form in terms of the building blocks. Okay, and then when we compare say for example, two products are the same, we only need to look at is their prime factorization, and in the final form, their numbers in terms of the prime factors are the same. So first, let's look at the first question, how to determine a number is a prime. And that actually, we're only going to using the definitions. We're going to check if such a number has any factors other than 1 and itself. And that seems really the only way. Okay? But to do that, there are certain observations we're going to make this process a little bit more efficient than checking all the numbers below that number. So let's see the first problem. Problem number 1. To check if 113 is a prime. Of course, actually or not. How are we going to do it? So we're going to check if 113 has any other factors other than 1 and itself, right? So let's see. First question, is 2 a factor? Well, we have learned for a number to be a multiple of 2, remember, the last digit has to be a multiple of 2, or the last digit has to be an even number. So for this, it's not. 2 is not a factor. Second, is 3 a factor? In other words, is 113 a multiple of 3? Remember the criteria that for a number to be multiple of 3? Well, that the sum of its odd digits has to be a multiple of 3. So for 113, the sum of all digits is 1 plus 1 plus 3 equals 5, which is not a multiple of 3. So this number itself, 113, is not a multiple of 3. Okay? Now, the third, is 4 a factor? And of course, you remember that for a number to be a multiple of 4, the last 2 digits has to be a multiple of 4, and 13 is not, so it's not a factor of 4. That's good. But actually, there's something more important here. Is 4 a factor? Or if equivalently is 113 a multiple of 4? We already know that 113 is not a multiple of 2. It's not a multiple of 2. 2 is not a factor. So if 113 is not a multiple of 2, can it be a multiple of 4? Of course it cannot. If a number is multiple of 4, so for example, if 113 equals 4 times something, a integer, this has to be a multiple of 2 as well, because 4 equals 2 times 2 and then times k. So then the 113 will be a multiple of 2, which is not true, so this cannot be true. Okay? So you see here, if I already checked a 2, I don't need to check anything of 4. Or using this logic, you can see I don't need to check anything of multiple 2. As long as 2 is not a factor, anything multiple 2 is not a factor. By the same token, anything multiple 3, I don't need to check anymore. So if you are paying attention, that means when we check all the factors, we only need to check all prime numbers. Non-prime numbers, I don't care, because non-prime numbers has to be a multiple of the prime numbers, and if we already check all the prime numbers, we don't need to check of the non-prime numbers. Okay, so we still need to check all the prime numbers. Okay, the fifth one. Is 5 a factor? Well, this is very easy. For a number to be a multiple of 5, the last digit has to be multiple of 5. So this is not. All right? Because of the factor 4, do we need to check is 113 a multiple of 6 or 8 or 9 or 10? No, we don't. It cannot be factor. I mean, all those numbers cannot be factor of 113. In other words, 113 cannot be a multiple of 6, 8, 9, 10. So, how about is 7 a factor? For this, there's really no good rule. No good rule. So you have to just divide 113 divided by 7 and to see if the remainder is 0 or not. And if you check it, it's not either. Okay? Now come to the next key step. And let me rewrite what we have checked so far. We want to check if 113 a prime number. So far we checked 2, 3, 5, 7, and 8 are not factors of 113. And by the argument of all composite numbers, we don't really need to check. We also know that 6, 4, 6, 8, 9, 10 cannot be factors of 113 either. Now, do we need to check a prime number of 11? Do we need to check 11? Is 11 a prime number? Of course, we know the rule, like how we check a 113 if a number is a multiple of 11 or not. But do we really need to? Do we need to? The answer is no. We don't need to. In fact, we don't need to check anything above 11 either. And here is the reason. So pay attention to this reason, because this involves a logic here. Let's say if 11 is a factor of 13. But since 11 times 11, it's already equals 121, bigger than 113, right? So 113 equals 11 times something. Let's say if it's a multiple of 11, so 130 has to be equals 11 times something, k, right? This k, because of 1, this k has to be less than 11, right? Because we know that 11 times 11 is bigger than 130. So if 130 equals 11 times k, this k has to be less than 11. But for anything less than 11, we know from here, there's no number that from 2 to 10 is a factor of 113. So this k does not exist, correct? So 11 cannot be a factor of 113 or anything bigger than 11 by the same argument. So here we actually are saying that we don't need to check any factor or any prime because we only need to check prime bigger than a square root of 113. Okay, and what is square root? Square root is a number such that, okay, let's first define what is a square, right? K squared equals k times k. Okay, this might be a little bit complicated for fourth graders or fifth graders. So let's hear. We don't need to check any prime numbers. Let's say bigger than, okay, let's just pick a number, 11, because 11 times 11 bigger than 113. So for this number, you have to estimate such that if you know that this number, 11 times 11, is already bigger than the number you want to check, in this case 113, then you can stop here. And you don't need to remember or trying to understand what a square root is. Okay? I'm just telling you that you can stop far earlier than checking all the prime numbers all the way to 113. So to recapture, to check a number, let's say n is a prime number or not, you need to only check two things: all the prime numbers or actually only the prime numbers up to some number k. And what's that k? You can stop if you realize k times k is already bigger than n. So let's using some concrete example, okay? Let's say n equals 1603. Then let's estimate what this k is. If when k equals 40, 40 times 40 is already 1600. So you can be very certain that you only need to check all the prime numbers 2, 3, 5, all the way to 40, which is 37. That's the last prime number you need to check. Once you check all those prime numbers, 2, 3, 5, all the way to 7, you are sure. And if none of them are factors of this n, then you are sure n is a prime. Otherwise, of course, n is not. Okay? So that's the basically the only way that to check if a number is a prime or not. And just to give you some understanding of the complexity of this procedure, you actually can see that it's fairly tedious, right? If the number n is very large, then to get to check if the number is prime or not, it's going to take a lot of time. And this is actually the foundation of cybersecurity these days. On the internet or like online bankings, there's a security measure that used to make sure the messages that you send on the internet is safe, because on the internet there's a lot of eavesdroppings. There are like malicious people there. They want to get other people's information so they can do bad things. And encryption is a way of making sure the messages are safe. And all encryptions are based on, I would say most of the encryption are based on this fact that it is very difficult to check if a number is a prime or not. And it is very difficult, if it's a not, to factor it. In fact, that most of the encryption mechanism uses a non-prime number, but it is a product of two very, very large prime numbers. I believe it's in the neighborhood of like 20 digits prime number times another 20 digits prime number. So for those bad people, good luck. I mean, they can using all their computation power, but it's going to be theoretically estimated taking them like a million years to crack that problem. So good luck, right? All right, so this is about checking a number is a prime or not. Now the next step we're going to talk about is prime factorization. So if a number is not a prime, how are we going to factor it into all primes? And this is better illustrated using an example. And from the example, you actually know that exactly what's happening. So prime factorization. Okay, let's choose n equals 112. So prime factorization works like the following. First, given this n, let's see, when we're checking a number is prime or not, we go for the smallest prime and to see if it's a factor. In here, n 112, you're actually in luck. The first number that a prime number is 2, right? And 112 is going to be a multiple of 2. So 2 times 56. Okay? So we'll get one prime out, and then we have this number left. And now we're going to continue on this number. Prime factorization is a recursive process. We just keep doing until we cannot do. So 2 is a prime, 56 is not a prime. So let's try check. 56, again, let's try to see what is the smallest prime number that is a factor of 56. In this case, is another 2 times 28. Okay, so these two parts are primes, and this one, we don't know yet if it's finished yet or not. We'll finish when this number is a prime. 2 times 2. Again, let's see what is the smallest prime number. It's a 2. Again, 2 times 14. And again, 2 times 7. All right, and you see for this 7, we know it's a prime, and we have all those primes, and these are the building blocks, and we're done. Now, just for notation and for convenience, that we're going to combine those 2 times 2 times 2 as using the powers. 2 to the 4 times 7. Okay, this notation might be a little bit alien to some of the younger kids. So let's see what a power means, okay? For any, let's say, a number a to the power n, in here we're going to focus on n as an integer. A to the n is really a definition. It really means a times a times a times a. How many a's? N a's. Okay? When you have n a's, multiply them together, multiply n a's multiply together, you using this short notation a to the power n to represent that. Is the notation clear? You know that mathematicians are a bit lazy in that sense, in terms of notation, but it's also a clarity. Using a to the n, you can save a lot of space, save a lot of writing, and save potential errors. And this is it's kind of similar to the definition of multiplication. Remember how we define multiplication. Multiplication is defined a times a times a. At least this is how we introduce a plus a plus a plus a. If there are n a's adding up, this is defined as a times n, right? So this is just, very similar to this. When you have a lot of multipliers, you're using this power. When you have additions of the same number, you use multiplication. Okay, so this part is just to give you what those power means. So you have 2 times 2 times 2 times 2, 4 2's. So we'll write it as 2 to the power 4 times 7. So that's one example of doing prime factorization. So again, prime factorization is a recursive process, and keep doing until you can do no further, and then you end up with a bunch of prime numbers, and then you're going to collect all the same primes together, make them into powers by using definition powers. So let's look at another example, and we're going to be introducing a bit of a different way to representing those prime factorization, even though that the fundamental ideas is exactly the same. Okay, so let's look at another problem, and actually the problem of 112 is the problem 5. So we're a bit of jumping ahead. Let's look at another problem. Let's call it a problem 9, which the page does not have. Okay, so let's jump around. Okay, let's factor 110. Okay, let's 210 and make it better. So another notation of doing prime factorization is using the tree structure. And basic idea is exactly the same. 210, first prime is a 2, and then you're left with 105. Okay, now for 105, 2 is a prime already. 105 is not, looks like. At least we need to try to check. So we'll see. 105, what is the smallest prime number? 2 obviously is not. 1 plus 5 is a 6, so it is a multiple of 3. So we can factor 3 out and left with 35. 3 times 35 equals 105. Now for 35, 2 is not a factor, 3 is not a factor, but 5 is a factor. And you have this. 5 times 7 equals 35. So end up to 10 equals, you collect all those things on so-called, this is a tree, and you collect everything on the leaves of the tree. Okay, mathematicians come up with all those very interesting terms, terminologies, you know, the names for these things. It's called the leaves of the tree, and 210 equals the product of all those leaves. 2 times 3 times 5 times 7. Okay, and you can verify this is correct. Okay, so this is called a tree representation. Of prime factorization. Okay, let's try another one, prime 10, and I'm going to be using a different representation for that, which is almost the same as a tree, but it has some advantage of later if you consider GCF. And let's look at a different thing, a different number. Let's say 236. Okay, I'm just coming up randomly. And this is using a long division kind of notation. So I put this, 236, what is the first prime? It's a 2. So come up with 118. Okay, and this again, another 2, becomes 59. Uh-oh, is 59 a prime number? Let's see. 3 is not a prime, 3 is not a factor, 2 is not a factor, 5 is not a factor, 7 is not a factor. Do we need to check 11? Because a squared is already bigger than this number, we should stop at 7. So this 59 is a prime number. So 2, and we're going to collect everything outside of those long division kind of things, right? Like that's the region that we don't need to include, and we can include this. So 236 equals 2 times 2 times 59. Okay, and this is the prime factorization, and we're going to write down, remember, we're going to collect everything the same into 2 to the power square times 59. Okay, and this representation is called long division. And it has the advantage of later, if we want to calculate GCF, you can put one number here and another number here, and you exactly do the same process, and the outside will be the GCF of these two numbers. But we're going to cover that later. Okay, so we talked about a few representations of prime factorization, and the whole idea is very, very simple. The prime factorization is really about you keep factoring every time you take out one prime, and the remaining you check if it's a prime or not. If it's a prime, you stop. Otherwise, you just keep doing it. Okay, so it's actually this whole process is self, obvious. So now let's look at a few numbers on the sheet. The first question, actually this is the second question that on the sheet, is there's only one, problem 2. There's only one even prime number, which is, of course, 2. Why? Why can't we have other even numbers? Okay, as usual, you should think about for a second, and I expect a lot of you already know, yeah, this is obvious, and you want to raise your hand. Great. So of course the reason is for any other even numbers, not 2. Let's say the even number is n. Even number means that it can be represented as 2 times another number k. So for n is not equal to, this k is going to be bigger than 1. So which means n has a factor of 2, which is not 1 or itself. So by the definition of prime numbers, this is not a prime. Okay? Clear, right? By the same token, which is less useful, is there's only one prime number ends with unit digit 5, which is 5. Can any other number, like something 5, a prime number? Cannot be, because 5 is already a factor, and for 5 to be a factor, and if the number is prime, 5 has to be, that number has to be itself 5. Okay, so these are very trivial facts, and but it can be also useful, and we'll see why. Let's look at problem number 3, and that's a kind of interesting problem already. It's non-trivial, but if you know what the basic properties of prime numbers, it's actually pretty easy. The sum of three prime numbers is 80. What is the maximum value of the product of 3? These 3 primes. Okay, as usual, think about this question for a few minutes. You can stop here, pause here, and once you get an idea, you can continue, or if you're stuck, you also can continue, and maybe you can stop as when I say something, and then you can stop if you think that you got a hint. And the important thing is always you try to work out the problem yourself. That's the best way to learn. All right, assuming you have taken your time, we're going to continue here. The sum of 3 prime numbers is 80. What is the maximum value of the product of these 3 primes, of these 3? All right, so we know that prime numbers, most of them except the one, are odd numbers. So if all those three prime numbers are odd, then see, odd plus odd plus odd, we know it's an odd. Cannot be 80, right? So you see that all those three prime numbers cannot be all odd, which means there has to be one prime number is 2. Okay, very simple, but it's kind of unexpected in a way, right? So 1 is 2. And when you think about those kind of questions, because there's no really ordering of those, you can think about, if there's no ordering, I can order them. And if I assume that these three prime numbers, A, B, C, I'm going to make them A less than B or less than C. So it's kind of from the smallest to the biggest. So that means A equals 2. That means B plus C equals 78. So now I'm actually really thinking about A times B times C. I want to get a maximum of this equals 2, because A equals 2, 2BC. Okay? And when you have B plus C equals 78, and you want to maximize B times C, well, that's something that we're going to cover later. But the fact you want to maximize this is you want the B and the C to be as close as possible. In geometric terms, is if you think this as a half of the perimeter of a rectangle, and you want to maximize the area of a rectangle, you want the rectangle to be as close as to a square. So you want BC to be very close. Okay, how close it can be? 34 and 39 and 39. Unfortunately, 39 and 39 are not primes. So what's the best thing you can do next? 37 and 41, does that work? Add up to be 78, and both of them are prime numbers. Well, you need to check them, but actually they are. So the best maximum value of the product is going to be 2 times 37 times 41. Okay, certainly not an easy question, but it uses the property that most prime numbers are odd except the 1. The 2 is a prime number, but it's an even number. That's the only one. And we're going to talk about one more question, and we're going to call it the end of this lecture. And most of the other questions I will leave as homework. So, one more question. Let's see. The question is problem number 6. I have a rectangle. Both the width and length of a rectangle are integer units. And the area of this rectangle is equal to 24 square units. Okay? The question is how many possible rectangles there are. So if we assume the width is W, the length is L, we know both W and L are integers, right? Given integer units. So we know that W times L equal 24. And we're really asking how many possible rectangles there are. It's really asking how many different combinations of W and L such that W times L equal 24. And this question is equivalent asking how many factors of 24. Because for every factor, it's going to have a pair of WL. For example, factor 1 this equals 1 times 24. For factor 2, equal 2 times 12. For factor 3, equal 3 times 8. Factor 4, 4 times 6. And depends on you count double counting or not counting, because there's also kind of written as 6 times 4. But this rectangle is regarded as the same rectangle as 4 times 6, right? So in fact, you only have 4 different combinations if you assume that W has to be, with a restriction, W has to be less than L. Okay, so this problem actually leads to how we're going to find out how many factors of, in this case, 24, but in general, how many factors 24 has. And in here, the general procedure is prime factor this. 24 equals 2 to the power 3 times 3 times 8, right? So the total number of factors actually has this formula of, it's going to equal this power plus 1 times this power plus 1, which here is power 1 here. So this totally will be 3 plus 1 times 1 plus 1 equal, totally have 8 factors. Now here we of course only have half of that different combinations because we're limiting W has to be less than L. Otherwise, if you don't have this limit, it's exactly will be 8 of such factors. This is kind of a leading towards a bit of advanced topic of understanding a number. How many factors does a number have? And that requires this prime factorization and counting those exponents in the prime factorization. And you see, because the prime factorization is factored into a product of all those primes exponents, and if you multiply two numbers together, it's kind of all those, because of commutative law, those powers going to add together, and you're left with all the primes from both numbers. So prime factorization is extremely useful, and I think that it's the most useful thing if you're trying to understand a product of numbers. And most questions will be around of that understanding. And that's it for this class.